All right, I'm just going to do a couple more examples of the unit step function, and then we're going to talk about why this is so important and what makes it so valuable. So in this first example, I'm going to take this function h of t is sine of t for t between 0 and 2 pi, and outside of this interval, it's going to be 0. And my goal is I want to write this in terms of unit step functions. Again, the very first thing you should do is just try to graph this thing and get a feel. Focus on the domain. So it's going to be 0, t less than 0, and 0 for t greater than 2 pi. And in between, it's going to be sine of 2 pi. So it's going to look like that. Okay, so it's basically it's going to be 0, 0, 0, and then from 0 to 2 pi, it's going to do a single wave, and then it's going to die out. So in terms of constructing this, what I'm going to do is I'm going to make this thing 0 for less than t equals 0. I'm going to turn on the sine function, and then when I get to 2 pi, I'm going to have to turn it off. So I'm going to subtract it using something that only turns on until I get to 2 pi. So my h of t, so my function is sine of t, and I'm going to multiply by the step function evaluated at t minus 0. Now this function is going to be 0 if t is less than 0, but if t is bigger than 0, it's always going to be sine of t. So at 2 pi, I need to subtract to turn it off, and I'm going to basically subtract a sine of t. Okay, let's do another example. Suppose I have this function, k of t is going to be 4 for between t 0 and 5. It's going to be 1 between 5 and 6. I got to be careful here. Now, there's going to be a small subtlety here. Notice this should be strictly less than, this should be less than or equal to. I'm going to leave it like this, and we're going to see that there's an error in the end. And then after t equals 6, we're going to get this function. So what does this look like? Again, focus on the domain first. As I go from 0 to 5, one thing's going to happen. 5 to 6, something else, and then bigger than 6, something else. So I know I'm going to have step functions that are going to start at 0. Then that has to be turned off at 5, and then a new thing has to be turned on at 5, and then at 6, that new thing has to be turned off, and then a new thing needs to, something else yet has to be turned on. Okay, so from 0 to 5, it's equal to 4. And then from 5 to 6, it's going to be 1. And then bigger than 6, so when t equals 6, this is 0, and it's going to decay to 7. That just keeps on going. So my k of t is going to be 0, but then at t equals 0, it's going to jump to 4. At t equals 5, that needs to turn off, so I'm going to subtract 4 times the step function at t minus 5. But then I need to turn on this 1, and that's going to turn on at t equals 5. At t equals 6, that 1 turns off. So I'm going to have minus 1 times the step function at t minus 6. But then I have to turn on the 7 minus 7e to the minus t minus 6. So my new function can be written like this. Now notice the way we've defined the step function, this is not correct at t equals 5. at t equals 5, this thing will give us 4, and that will still be 0, and everything else will be 0. So, oops, sorry, I got that wrong. At t equals 5, this will have turned on. I'll have 4 minus 4 is 0, and this will be 1. Everything else will be 0. So this is actually going to be 1. So at these endpoints, the way I've defined it here is not going to be correct. However, if I'm using this in a differential equation, it's not going to matter, because what happens at a single point isn't going to make that big a difference, right? The integral underneath a single point is going to be 0. So I can kind of sweep that under the rug. All right. So the question now is, why do we bother with this? And it turns out, if I take the Laplace transform of a function evaluated at t minus a times a step function at t minus a, that this is going to be nice in some sense. Having said that, you need to be very careful. There's a t minus a there, and in the examples we've seen before, our functions don't look like that, so you have to do some algebra to make things look like this, where this number here has to match that number there. So that's going to cause some problems later, so be very careful about that. All right. Let's look at this thing, though, and see what we can do with this. From the definition of the Laplace transform, I just take my function, multiply by e to the minus st, and then integrate from 0 to infinity with respect to dt. Here's the thing. If t is less than a, this thing is 0. So I can write this as the integral from 0 to a plus the integral from a to infinity of the exact same thing. Right? So what is this? This is taking advantage of this idea that if I'm integrating some function, I'm basically, it's a definite integral. I can find the area from 0 to a, and then find the area from a to the right, and just add those, and that's going to give me the total area. Having said that, from 0 to a, this step function is going to be 0. So this whole term in here equals 0. So that means the Laplace transform of f of t minus a times the step function at t minus a is equal to the integral from a to infinity of f of t minus a times the step function at t minus a e to the minus st dt. And I know that that's equal to 1 if t is bigger than a. So I can just replace that with 1, and I get this following thing. All right, so what do we have? So at this point, we have Laplace transform of f of t minus a times the step function at t minus a is equal to the integral from a to infinity of f of t minus a times e to the minus st dt. And now we're going to do a trick here. And the reason we're going to do a trick is because we would like to write this in this form, because this is the definition of the Laplace transform of some function. And that's not quite what I have here because of this a. So let's focus on that. I'm going to do a u substitution. If I let u equals t minus a, then du is going to equal to dt. In terms of my bound, so this bound here is t equals a. If I plug in t equals a, u is going to be a minus a is 0. I need to be careful. And as t gets big, u gets big. So this says then the Laplace transform of f of t minus a times the step function of t minus a. So now, I have dt is equal to du. T minus a is equal to u, so that becomes f of u. T, what is t? Looking at this, t equals u plus a. So I get that in there. And now for my bounds, when t is equal to a, u is equal to 0. And as t gets bigger and bigger, u gets bigger and bigger. So let me rewrite this. Let me multiply that s through. And notice this has nothing to do with u. So I can pull that out of the integral. And so this is e to the minus su times e to the minus sa. And that I can yank out. And so this becomes e to the minus s times a times the integral from 0 to infinity of f of u times e to the minus su du. And this is the definition of what it means to take the Laplace transform of a function. So what this says is the Laplace transform of f evaluated at t minus a times a step function at t minus a is equal to e to the minus sa times Laplace transform of f. And again, be careful about how you define what f is, because you're not given f in practice, you're given f evaluated at something, and you've got to backtrack to figure out what your original f is. Okay, so why is that a big deal? That is a big deal because now if I've got a situation where I've got some force that goes off to on and then off, or if a battery goes from off to on to off, if I write things in terms of unit step functions, then I can just take the Laplace transform, solve the differential equation like I normally would, and everything is good. Just as an example to see how these things work. Suppose I have the function t minus 4 to the 6th times a step function evaluated at t minus 4. So if I have to take the Laplace transform of this thing, step. So before we would have to go through back to the definition and just redo the integral and work with that integral. But in this case, my g of t minus 4 is t minus 4 to the 6th, which means that my g of t just says whatever you give me, I raise it to the 6th. So the Laplace transform of t minus 4 raised to the 6th times the step function at t minus 4. So in this case, my a is 4. That's going to be e to the 4s. Oops, I got to be careful. There's a minus sign, right? I need a minus there. Times the Laplace transform of g, which is t to the 6th. So this becomes e to the minus 4s times 6 factorial over s to the 7th power. Which means then, if you know that the Laplace transform of some function is e to the minus 4s times 6 factorial over s to the 7th, then you can work it backwards and say, oh, that means my y was t minus 4 to the 6th times the step function at t minus 4. And there was no ugly integration or working with crazy stuff. One last example. Suppose I have the function t times the step function evaluated at t minus 2. So what's going on with this function? This function is going to be 0 until I get to t minus 2. T equals 2. At t equals 2, it's going to jump up to t, which is 2, and then just increase linearly ever after. Okay. The problem here, so let me do this. The Laplace transform of g evaluated at t minus 2 times the step function at t minus 2 is going to be e to the minus 2s times the Laplace transform of the function. I am given t, and it doesn't look like t minus 2's everywhere. So I need to write t so that everywhere I see a t, it looks like a t minus 2. Right, I want to see that everywhere, because then that's going to, my g is just going to be replacing that with a t. This is not equal to this, but if I take my t minus 2 and then add 2, this is now equal. And so this means that if I write my Laplace transform, instead of t, if I write it as t minus 2 plus 2 times the step function evaluated at t minus 2, then I can write this in two pieces. This becomes the Laplace transform of t minus 2 times the step function at t minus 2 plus 2 times the step function at t minus 2. So this is h of t is t, because h evaluated at t minus 2 is just t minus 2. This is just g of t equals, sorry, let me rewrite this. G of t minus 2 is 2, and g of 2 is going to be equal to 2. So that means then that this Laplace transform is going to be e to the minus 2s times the Laplace transform of t plus e to the minus 2s times the Laplace transform of 2. Laplace transform of t is 1 over s squared. Laplace transform of 2 is 2 over s. So I can immediately see then that if I had this, if I had a function whose Laplace transform is this, I immediately can see that this I can write as the sum of two step functions, where this is g of t is t, but I'm going to have to evaluate it at t minus 2, and this is g of t, sorry, this is h, this is the function is equal to a constant, and that constant is equal to 2.